Let's try that again. Hi, Charlotte.
Hi. Sorry, I know you are responsible.
I'm waiting for for some news. What can I help you with?
I did have a couple questions about the chapter 9's homework.
Okay.
If maybe we could go over that a little bit before moving on to gas laws.
Sure. Let me open up the homework so that when you ask the question, I can see what you're asking. How's that sound? Is that all right?
Yeah.
How's the weather up there?
It's really nice today.
Well, that's great. I hope you get to enjoy some of it.
I won't.
Today, I guess it was very foggy last night or something because the roads were all wet this morning. Okay, module 9. Homework. Okay, what number?
Number 6.
Okay, so I'm going to start recording now.
I think you already did.
Oh, apparently I did. Okay, and I'm going to do a new screen share so that everyone can see the problem that we're looking at. Nitrogen can ionize to form N2 plus or add an electron to become N2 negative 1. Using molecular orbital theory, compare these species with regard to electron configuration, magnetic character, net number of sigma bonds, net number of pi bonds, bond order, bond length, and bond strength. Now, let's take a look then. Okay, I'm going to do a new share. Oh, and before we do the new share, I'm going to write down electron configuration. I'm going to write down magnetism instead of magnetic behavior. I'm going to write down net sigma bonds. You can't see what I'm writing because I'm just writing these down before I switch screens.
I was really just curious about when you ask about bond order, bond length, and bond strength. Are we
Yeah, that's a common question. And when we get there, you'll see what I may head off that question. So let's take a look here. So we're supposed to compare all 3 of these, N2, N2 plus, and N2 minus, okay?
Mm-hmm.
Okay, so first of all, let me do my new share. Oh.
Did you have office hours yesterday?
No one called in, so I didn't post anything.
Okay.
Let's see. There we go. Okay, so these are the questions for N2. Can you see the N2 up here next to my finger?
Mm-hmm. Yeah.
Okay, I can't see it because my Zoom bar is over that. So we're going to look at N2, N2 plus, and N2 minus. And what we want to know is how many electrons these guys have. Nitrogen has, oops, hang on a second. I got this ugly thing on my screen here that I'm trying to get rid of. There we go. Okay. Nitrogen is element number 7, right?
Yeah.
So that means we're talking 14 electrons. N2 plus 1 would have 1 less electron so that it could be positively charged, and N2 minus would have 1 more electron. So that's how many electrons we're looking at. And because this one is nitrogen, which is right before oxygen, we're going to use the Christmas tree, right? Instead of the palm tree.
Yeah.
So the Christmas tree is like this. And I did the little 3 blind mice, right?
I don't know. You didn't sing it this time.
3 blind mice, 3 blind mice. See how they run. It's perfect, isn't it? Sometimes in class, I really try to sell the idea that that nursery rhyme was because of chemists. Okay, now the outsides are pi 2p's. And for the pi 2p's, the one above is a 2p star, right?
Yeah.
So for every regular 2p, there's a 2p star. And the 2p star is called an antibonding. And the one without a star is called a bonding molecular orbital. All of the ones up the middle are sigmas. And you got a 1s, 1s star, 2s, 2s star, and a 2p, 2p star. And I think what I'm going to do is, you see these 3 here? I'm going to leave those off just because it's getting crowded in here.
Yeah. Okay.
So this one's going to be N2, this will be N2 plus, and this will be N2 minus. So I've got to put 14 electrons in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So notice when I do the 9, 10, I go from one pi 2p to the other pi 2p before I double up. That's just to get into good practice.
Right.
So 10, 11, 12, 13, 14. So that's N2. N2 plus is going to look exactly the same except for one less. 1, 2, so that's 10, 11, 12, 13.
Mm-hmm.
And N2 minus is going to be one more. So there's my 10, 11, 12, 13, 14, and one up here. Now, I wish I had more room here, but I don't. So what I'm going to do is I'm going to take all of this and write it up here. Actually, I'm going to do this. For the electron configuration, here's what N2 is going to look like. Sigma 1s 2, sigma 1s star 2, sigma 2s 2, sigma 2s star 2, pi 2p 4. We combine these together because they are the same energy.
Okay.
And then sigma 2p 2. So that's for N2.
Would it
N2,
be okay to write core in brackets and then the remainder?
I don't have to write core because I actually wrote them out for the core. These are the core right here.
Yeah, so instead of writing that out, would it be okay to write core in the brackets?
Yeah, I'd be fine with that, but you don't really save a whole lot of digits. That's why I didn't do it. Now, what I'm going to do here, just for brevity of instruction, N2 is going to be exactly the same, except for it's going to be sigma 2p1.
Right.
And N2 negative is going to be the same, except it's going to be pi 2p star 1. Now notice in this case, the superscript default is not 1. You write the 1 when it's there. because normally we don't write ones, right?
Right.
But here you want to write the ones. Okay, now when we look at magnetism, which I'm going to say is mag, and we look at net sigma bonds and net pi bonds, bond order, bond length, and bond dissociation energy for N2, N2 minus, and N2 plus. When we look at magnetism, everything is paired in N2. So here the magnetism is diamagnetic. Here you have an unpaired one, and here you have an unpaired one. So these are both paramagnetic. Are we good on those?
Yeah.
Okay, net number of sigma bonds. So I'm going to focus on these guys in the middle and ignore the guys on the sides. And 2 in an anti-bonding cancel 2 in a bonding.
Mhm.
So here, due to the 1s, there's no sigma bonds. Due to the 2s, there's no sigma bonds. Due to the 2p, we have 2 electrons in an orbital. 2 electrons equals 1 bond.
Okay.
So for this guy, the net number of sigma bonds is 1.
Okay.
For the pi bonds, I'm going to look at the outside only. Here, those 2 electrons equal 1 pi bond. And the 2 electrons that I'm pointing at on the left equal 1 pi bond. Again, 2 electrons, 1 bond. So here I've got 2 pi bonds and nothing to cancel them.
Right.
So I've got 2 net pi bonds. Now, if we look at N2 plus, you can see that I'm going to have all of my sigma bonds canceled except for half of a sigma bond.
Okay.
1 electron is half of a bond. So I have half of a sigma bond. And I have 2 pi bonds.
Great.
Now, for N2, I'm actually going to have a full-on sigma bond, right? But if I look at the pi 2p bonding electrons, there's 4 of them, and one of them gets canceled by a pi star 2p electron.
Yeah.
So what's my net number of pi electrons? It's 3.
Can you repeat that?
What's my net number of pi electrons? It's 3.
Okay.
So
Yeah.
net means, considering everything all together, right?
Okay.
So
Yeah.
I've got 4 minus 1, 3.
So
How many bonds is 3 electrons?
1.5.
1.5, or I wrote 3 halves, same thing.
Okay.
Okay, now for bond order, we simply add these sigma bonds and pi bonds together. So the bond order for N2 is 3, N2 minus is 2.5, and N2 plus is 2.5.
N2 minus is 2.5?
Yeah, 2.5 is 2.5,
Okay.
right?
Yeah.
And 1 and 1.5 is 2.5.
Okay.
Now, bond length, we're going to say that we know that the more bonds you have, the shorter your length, right?
Yeah.
So I'd expect this to be the shortest and these two to be the longest. Now, why are these two the same length? Because they're both a 2.5 bond order.
Right.
Now, bond dissociation energy. This is going to be the highest, and these guys will be the smallest. Because the larger your bond order, the harder it is to break that bond.
Yeah.
And when you have a 2,5 and a 2,5, we're not going to say, well, this one's got to be stronger than the other. We're going to say, hey, these should be about the same.
Okay.
And that's how you would handle number 6.
Okay. That's what I was thinking. I had all of that.
Well, I'm glad we confirmed it, and that's got to make you feel better.
I don't know why the net bonding thing kind of doesn't come as easy as I feel it should, but that's
Well,
okay.
your fallback could be just to use the formula. So when you look at sigma bonds, you can do 1/2 of the bonding electrons minus the anti-bonding electrons.
Yeah,
So pi bonds, the same thing, 1/2 bonding electrons minus anti-bonding electrons. And when I say bonding electrons, what type of bonding electrons?
sigma,
Sigma. And here, what type of bonding electrons?
pi.
Pi.
Okay.
So not all of the bonding electrons, just the sigma. So if
Right.
we wanted to rewrite these, we could write it a little better and say for the sigma bonds, we could say 1/2 of the sigma bonding electrons minus anti-bonding electrons. So we could sneak the little sigma in there, right?
Right.
And the same with the pi. And that's how
Okay.
you do it. So that's number 6.
Okay.
Do you have another one that you'd like to look at from that homework?
No, I don't think so. I mean, I feel like they kind of ask the same thing.
You know what? Chapter 10 is 2 topics, valence bond theory and molecular orbital theory.
Right.
And the toughest thing about valence bond theory is that you have to remember the hybridization and how do pi bonds arise, right? That's the tough part.
Yeah.
What's tough about molecular orbital theory? And the answer is Christmas tree or palm tree. Which one do you use where?
Right.
And the answer is halfway through the pea subshell. Use a Christmas tree until you have to use the palm tree.
Right. So the lower energy ones use the Christmas tree.
Right. For the first half. So that would be what? Beryllium, Be2, C2, N2.
Mm-hmm.
And you know, if you look at that, Be, C, and N versus oxygen, fluorine, and neon, here, these 3 use the Christmas tree. And because Christmas trees look like this, right?
Mm-hmm.
And that's the general look of this guy. That's why I call it the Christmas tree.
Yeah.
And here I call these the palm tree, but maybe you want to call it something else like, I don't know, well, you could call this one the flower, because flowers generally have this type of look to them, right? So here's the flower. So you could use F and C as your keys to the shape. C, Christmas tree. F, flower.
Oh,
You know, these are things that not only I use as tricks to help me remember things, but a lot of people who don't have good memories use these types of tricks. So it goes a little bit beyond the, what is it, the anagram, not the anagram, the have no fear of ice cold beer. What do you call those things?
mnemonic.
It goes a little bit beyond the mnemonic. It's more of a, sometimes it's like a visual thing.
Yeah.
So different people have different tricks for doing this. You could also use the O, because that looks like an O, doesn't it?
Yeah. It's round.
So you could use the C for Christmas and the O for the one that's more rounded at the top. You know,
Okay.
different tricks for, tricks aren't just for kids anymore. Which, this is kind of stupid, but I was watching that. Have you ever seen that movie called Ted, about the teddy bear?
Yeah.
Well, do you know who Liam Neeson is?
Yeah.
So he's plays kind of like a pretty daunting character, tough, right? So I remember one of the movies, he came in there and he bought a box of tricks and he asked Ted, can I buy these? And Ted says, yeah, absolutely. And he goes, well, I'm not a kid, you know. And he goes, yeah, it's fine. You can buy them.
Oh my gosh.
And then he said something like along, and no one will come looking for me. Oh, no. I promise you. So tricks aren't just for kids. They are for adults and Liam Neeson. All right, what else can I help you with? Do you want me to just do some problems from the back of chapter 10?
Can we move on to gas, the next chapter, gases and their properties?
That's chapter 10.
Okay. Oh yeah.
I just posted a video doing problems 2 through 20.
Of chapter 10.
Yeah, so how about we start off with number 22? Is that all right?
Sure. Yeah.
Okay. Okay, so here's number 22. Can you read that all right?
Yeah.
Okay, what mass of helium in grams is required to fill a 5-liter balloon to a pressure of 1 atmosphere and 25 degrees Celsius? So here, there's no change in pressure, change in moles, change in temp, or change in volume. Because of that, we're going to use the ideal gas law, PV equals nRT. Now, for PV equals nRT, they want us to know what mass of helium in grams is required. So what we're going to do is we're going to calculate the moles. And then once we have the moles, we're going to use the moles to calculate the grams using the molar mass of helium, okay?
Okay.
So to calculate the pressure or the moles of gas, we need the pressure, and the pressure is 1.1 atmospheres. We have the volume, it's 5.0 liters. We have the temperature, and it says 25 degrees Celsius, but we never use degrees Celsius in gas laws. We always use Kelvin. So I'm going to write that we have 25 plus 273.15, which is 298.15 K. And I'm going to put a little arrow pointing to the 8 because that's where I would round this if it were done.
Okay. Mine's close.
Okay. Now, what am I going to use for R? I'm going to use the R that has the unit of atmospheres in it. So I'm going to use 0.08206 liters atmospheres per mole per K.
All right.
So again, my strategy is first calculate the moles and then then calculate the grams. Fair enough?
Yeah.
Okay. So I'm going to get N is equal to 1.1 ATM and then 0.08206 liters atmospheres mole K. Now, this is something you may remember from your previous chemistry class. We used 0.0821. In this class, we're using 0.08206 because, you know, we can do a better job here in this class. Let's see what we can do. Because this would round to 0.0821, correct?
Yeah, I was wondering about, so N equals PV over RT, right?
Yes.
Okay.
So how did I do this? I divided each side by RT.
Yeah, but you have R in the numerator down there.
What's that?
You have R in the numerator now.
Oh, thank you.
So I'm all confused.
Oh, I see what you're saying. Yeah.
Okay. So we want 5.0 liters
And
there.
I guarantee you that when I started crossing units out, I would have found out I had a problem, right? Because
Yeah.
would atmospheres cancel?
No.
No. So that's the beautiful part about putting your units in with your problem is you quickly find out that you don't have it set up correctly.
Yeah.
But you know, it's much better if you just avoid that altogether, right?
Yeah. Okay.
And that's why I always insist you put your units in with your calculations so that you can see it all does work out.
Yeah, because we're just left with mole now.
Yeah, so we can see that the K's cancel, the atmospheres cancel, the liters cancel, and the mole is what you're left with. And you know about the cross the line, change the sign, right?
Mm-hmm.
So here, if we cross the line, we change the sign, then cross the line again, and we change the sign back, and you get moles.
Mm-hmm.
And then there's always estimating. So here's the way I would estimate this. I always think of this as being 0.1, not 0.08. So I round up quite a bit.
Okay.
What's 0.1 times 300? So that's 1/10 of 300, which is 30, right?
30.
And now it's not really 30 because this is not 0.1. So instead of 30, you say, well, it's 25.
Okay.
What's 5? And 1.1 times 5 is 5, right?
Yeah.
So what's 5 over 25?
5.
1/5, right?
1/5.
So 0.2. Our answer should be around 0.2. You'll see on my video for the first 20 or 10 problems, I made an estimate of like 115 and the calculator came out at 135, and I'm not usually that bad. And it turned out instead of using 125, I used 152.
Oh.
I did a little dyslexic type thing, I guess. I never thought of myself as being dyslexic, but maybe I am.
So I remember a Tony's law.
Yeah. I talk about that in those first problems too. There's no such thing as Tony's law.
I know.
So I get 0.22 moles.
Oh.
So I would expect to see, well, let me finish this off now. So now we're going to take this answer and turn that into grams. So I actually get 0.2248 moles. So that's without rounding. And I'm going to multiply times 4.01 grams per 1 mole because that is the molar mass of helium. So now I get 0.8992 grams, which I'm going to round to 2 significant figures, which is 0.90 grams of helium. So I would like to see, of course, all of this as your work.
Okay.
Now, there is, I believe, another way to do this, and that's the following. So here's the ideal gas law, and that's when you don't use Tony's law, which is nothing changes, right? Now, molar mass is the mass of something divided by the moles of something.
Yeah.
So if you had 4.01 grams of helium, you would have 1 mole of helium. So that's the molar mass of helium. Are you with me?
Yeah.
Okay. Another way to say this, though, is that N is equal to the mass of something divided by the molar mass, right?
Yeah.
I'm going to take this and put it in over here. And now we have PV is equal to molar mass times RT over molar mass. Okay?
Okay.
Now what I'm going to do is I'm going to do this. PV capital M is equal to lowercase m RT. And then I'm going to do PV over RT is equal to little m over, oh, I'm going to do PV over RT is little m over big M. Nope, over V. That's what I want to do. So PM over RT is equal to little m over V. You with me?
So that's density.
That's density. So that is the formula for density is equal to PM over RT.
And
Now,
PM and
I'm going to tell you, this is a formula that no one memorizes. So this is a perfect formula to put on your index card.
Okay.
But also, if you remember that density is mass over volume, we could probably do this problem again. And what would we be solving for here based on the problem?
For
We're
density.
solving for little m, v. Oh, I wrote that incorrectly. That should be an m there. Am I solving for little m, v, big M, P, R, or T?
Little m.
Little m. So here we get little m is equal to P big M RT times V, right?
Yeah.
So the pressure, 1.1 atmospheres. The molar mass, 4.01 grams per mole, right?
Yeah.
The volume, 5.0 liters. R, 0.08206 liters atmospheres mole K. And the T is 298.15 K, right?
Yeah.
So here you can see that the moles cancel, the atmospheres cancel, the liters cancel, and the Ks cancel. The only thing that doesn't cancel is grams. And so what's neat about this method is that you're getting the answer with one calculation instead of two.
Yeah.
And guess what number we're going to get when we put all these together?
0.90.
0.90. And here it's real easy to see, hey, I only get two zig figs because of those two numbers, correct?
Yeah.
So this is a nice formula to have where I might actually have it written out this way and include that M over V, because sometimes it doesn't kind of hit you at heart that density is mass over volume.
Yeah.
But this is a real neat equation if you're given this type of information and you want to calculate any one of these 5 things, because R is always the same, right?
Yeah.
But they might say, what's the molar mass? And you just plug in the mass, the volume, the pressure, and the temp, and boom, you get the molar mass. Or you might be asked the question, so which gas is it? Oxygen, nitrogen, or whatever, right?
Mm-hmm.
And you're wondering, well, how are those gases different? Well, they're different by molar mass. So you plug in the numbers, you get the molar mass, and you say, oh, the molar mass is 32, it must be oxygen. Or the molar mass is 28, it must be nitrogen. Or the molar mass is 36.5, which means it's HCl. You with me? But
Yeah.
that might be a way to distinguish is by molar mass. So this is a very useful equation and one that I would put on my index card.
Okay.
Okay, that being said, let's go ahead and move along. I probably kicked that horse a little too often. What is that saying? No point in kicking a dead horse?
Yeah.
And why do they say that?
I don't know, Tony. It's already dead.
Right. You only kick a live horse to get it going, right? The dead horse ain't going to go nowhere. I've been horseback riding, I think, twice in my life, and I did not dare kick the horse either time because the way they were walking at the slow pace was more than enough for me. I did not want that sucker galloping or trotting or anything. Okay. Because they're scary. Those things are huge. They are just huge. They're enormous animals. Okay, diethyl ether, C2H520, vaporizes easily at room temperature. If the vapor exerts a pressure of 233 millimeters of mercury in a flask at 25 degrees Celsius, what is the density of the vapor? This sounds like one of those ones that's just built for this equation, doesn't it?
Yeah, I asked about density.
Yeah. Now, what does C2H520 mean? It means C2H5O, C2H5. So here you have two of these attached to oxygen, and we know oxygen likes to make two bonds. So what I did here is I kind of put one on the left of oxygen, one on the right of oxygen, like you would do for H2O, which we know is HOH, right?
Yeah.
So I did the same thing here. And I did this so that we understand that the molar mass of this is going to depend on 4 carbons and 10 hydrogens and 1 oxygen, right?
Right.
So that is to make this Tony proof so I don't screw up and say, oh, there's 2 carbons. There's 4. So 4 carbons is 48.04 because each one is 12.01. 10 hydrogens is 10.10. And actually, it's going to be 10.1 without that 0 there. And 1 oxygen is 16.00. When we add these all up together, we get 5874.14 if I added it up correctly. So for the density, we want the pressure, 233 millimeters of mercury. The molar mass is 74.14 grams per 1 mole. And this is only good to this one here, but we're going to carry the extra 4 along for the ride. The R I'm going to leave off for just a moment. And for the T, we're going to say that we have 25 plus 273.15, which would be 298.15, good to the 8. Are we good so far?
Yeah.
Now we have 0.08206 liters atmospheres per mole per K. There's another R that has millimeters of mercury. And to get that, we would multiply by 760 millimeters of mercury per 1 atmosphere. And let's see what this comes out to be.
Would it have been okay to converted it before plugging it in?
Yeah.
Okay.
But we end up with 62.37. So 62.37 liters, millimeters of mercury per mole per K. So honestly, these are things that I would put on my index card because I don't want to try to remember that. And I don't want to try to remember 62.37 because I memorized 62.4, only 3 significant figures. But in this class, we go the extra digit.
Okay.
So, you know, on my index card, I would write this down. This has all the units here. And I'd write this down and understand, oh, that's the one with millimeters of mercury.
Okay.
Okay. So here, if we estimate the answer, is it pretty clear that 74 goes into 298 about 4 times?
Yeah.
Okay. Is it clear that 62 goes into 233 about 4 times?
Mm-hmm.
So you got 4 over 4. What's the answer?
1.
1. The answer should be about 1. Looks to me like 1 gram per liter,
Gram. Yeah.
because millimeters of mercury cancels,
And
moles cancel, K's cancel, but I'm going to circle the G and the L because they never canceled. So it's going to be grams per liter. And that's a common unit for density of gases, not grams per centimeter cubed, not grams per milliliter, but grams per liter, because you need a large volume to get a gram of gas.
yeah.
So let's see what we get. You will probably already have an answer, right?
No, I'm actually writing on my note card.
Oh,
For the exam, doing the conversion,
yep.
between for the R constant, should we show that work, or is it okay if we write these on our note cards? And
I would write this on my note card and use that if I need it.
okay,
I would write this on my note card and use that if I need it.
so but we don't need to show that conversion.
No, because most people memorize both of these.
Most people.
Yeah, just like you memorize other things like 1 centimeter cube equals 1 milliliter. No one writes that on their note card because they memorize it. Just like most people don't write 0.254 centimeters equals 1 inch because you just memorize it. So these are common ones to memorize. Now, because I'm asking you guys to go the extra mile and have 4 zig figs here, you might want to write this on your note card, but do you really need to write the units of this on your note card? Or can you just kind of remember that, oh, this is the one that's liters, millimeters of mercury per mole K. I mean, the only thing that's different is the pressure, right?
Yeah.
So that's why I would only write the number down and I would know what the units are.
Okay.
Okay, so my answer here with 2 significant or 3 significant figures is 0.929 grams per liter. So this is the work I would expect to see. And no, I don't expect to see you calculating this. I expect you to have it memorized or written on your note card.
Okay.
So anytime you see something that deals with density, you know you want to go to this equation.
Right.
Okay.
$26.
Yes, 26. Oh, I've told you the joke about chloroform, haven't I?
I don't remember if you did.
It's a common liquid used in the laboratory. We use it as a solvent in organic reactions. And
Okay.
it's the stuff you see in spy movies where they pour it out of a brown bottle onto a handkerchief and they put it over someone's mouth and they knock.
Yeah.
Well, it turns out that chloroform's a carcinogen, which means it causes cancer, right?
Right.
So spies aren't allowed to use it anymore because it could cause cancer. Because, you know, it's a health hazard.
Yeah, I get it.
That would make a cute little skit on some comedy show, wouldn't it? Okay. You know, then they say, oh yeah, we better use the blackjack instead. Knock them out. And then you can have a whole nother bit about how that could cause a concussion and maybe brain damage. You're like, so what do we do? Ah, screw it. Let's go work at McDonald's. Okay. It vaporizes readily. If the pressure of chloroform vapor in a flask is 125 millimeters of mercury and the density is blah, what is the molar mass? So boom, we're going to use that D is equal to PM over RT, right?
Right.
And we're solving for M, which is the molar mass. So we get M is DRT over P.
Right.
Now, the density, because of R, we want it to be in grams per liter. So here we have 1.25 grams per liter, which is nice. It's already got the units we want. I'm going to leave R out of it for the moment. The temperature is going to be 273.15 plus 25.0, which gives us 298.15 K, right? And over P, the pressure is 195 millimeters of mercury.
Right.
So do I want to use the R that has millimeters of mercury or the one that has atmospheres?
Millimeters of mercury.
So we're going to use the 62.37 liters millimeters of mercury over mole K. And see, just from the last problem, I've already memorized that number.
Okay.
Okay, let's estimate the answer.
Wait, we're going to end in grams, right?
Well, let's find out. Millimeters of mercury cancels with millimeters of mercury. K cancels with K.
Mole.
Liters cancel with liters. Do we end up with grams?
Grams per mole.
Grams per mole. Good. Should molar mass be grams per mole?
Yeah.
Okay, then we're in business. Okay, so again, because we have the units there, we quickly found out that we did put everything in there correctly.
Yeah.
Okay, so let's estimate the answer. How many times does 62.37 go into 195?
3 times.
How many times does 3 go into 300? 300 divided by 3.
30.
No, come on. 300 divided by 3.
10.
100, right?
Yes.
Okay. 100 times 1.25.
100 times 1.25.
Yeah.
125.
Boom. So our answer should be about 125. And I get 119, which isn't a bad difference between our two numbers. So that's the molar mass of this gas. And chloroform, I happen to know, is CHCl3, which is 12.01 plus 1.01 plus 35.45 times 3. And let's see how close this is to the real number. And I get 119.4 for the real number. So spot on, right? Okay. So any questions about this one?
Nope.
Okay. A 0.130 gram sample of a gas with an empirical formula. And I'm going to be honest, when I see grams, I'm almost thinking, this is going to be one with density, right? because density is grams per milliliters or grams per liter.
Uh-huh.
So, my radar is up for using D equals PM over RT. So a 0.0130 gram sample of a gas with an empirical formula of C4H5. So that means it could be C4H5, it could be C8H10, it could be C12H15. Some variation of that proportion, the real formula that is placed in a 165 milliliter flask. And I'm almost thinking, you know what? I bet they want us to figure out what the real formula is by getting its molar mass and then seeing which one of these it matches. I bet you that's what the problem is, right?
Yeah.
So it has a pressure blowout. What is the molecular formula? So what is the molecular formula of this? What's 4 times 12?
84. 48.
48.
Yeah.
I think the problem is when you did the problem in your head, you were looking at the mirror image of the answer. That's why you said 84. I've seen this before. And what'll help is when I see you look up to the sky for the answer. For people like you, it helps if you cross your eyes when you look up, because then you'll see the real answer.
I'm not doing that.
But that's the problem. If you cross your eyes, it'll switch it back to correct.
Okay.
It'd be so great if little things like that could fix some of the issues we have, right?
Oh my gosh.
Okay, so that's 48. And what's 5 times 1 for hydrogen? And 48 plus 5?
53.
Okay. So what is the mass of C8H10? It's 106, right?
Yep.
Because you just double it. And for C12H5, you triple it. So you get 159 and so forth and so on, correct?
Mm-hmm.
And here, this one, I would double that one and get 212. So I've got a good chance of figuring out what the molecular formula is based on this. And I'm going to use the D is equal to PM over RT. And what am I solving for here? I'm solving for M, which is DRT over P. And the density is 0.0130 grams. Now here, we don't want to use milliliters, do we? So we're going to take our 165 milliliters and multiply by 1 times 10 to the minus 3 liters over 1 milliliter. So the milliliters cancel, and we get 0.165 liters. So that's the density. The R, I'm going to leave off until I figure out what pressure I'm going to be using. For the temperature, I'm going to use 22.5 plus 273.15, which is 295.65. And the pressure, they're giving me 13.7 millimeters of mercury, which is a very low pressure because room pressure is 760. This is a lot less than that. So I think I want to use the 62.37 millimeters of mercury per mole per K in this problem. Does that sound about right?
Yeah.
Okay. Liters cancel. Millimeters of mercury cancel. K cancels. Grams and moles did not cancel. And here, when I do the estimate, this one is a little tougher because of the 0.165 and the 0.130. Those are really small numbers to work with, but I'm going to give it a shot anyways. So I'm going to say 13 goes into 62 about 5 times. I'm going to say 5 times 0.013 is like 5 times 13, which is around 60. So I'm going to say 0.6. And if this is actually 0.06, and 0.06 over 165 is like 1/3 of that. So I've got 1/3 of 295. So I think my answer is about 100-ish.
Okay.
So let's see what we get. 0.0130 times 62.37 times 295.65 divided by 0.165 and also divided by 13.7. And I get 106.
Oh, sorry. Yeah, I was going to ask you about that. So did you just put the 0.165 in the denominator?
Yeah. So what I did is I thought, this is the way I think of it. If I were just doing the top, couldn't I just multiply everything on top and then divide by 0.165 and get my correct answer?
Yeah.
Okay. And then if I got that answer, could I take that answer and divide by 13.7 and get the right answer?
Yeah.
So that's what I did. So I'm not sure if you can see my calculator. I did the 0.0130 time, 30 times 62.37 times 295.65. So that's all these things multiplied. And then I'm going to divide by 0.165, and then divide by 13.7. So that's the way I did it. No parentheses or anything.
Okay.
Kind of like I know how my calculator works, so I'm going to put the numbers in here so that it works out nicely. And I get, let me change that so it's easier for you to see the answer. 106.
Okay.
And I know it's 3 zig figs because this is 3, this is 3, this is 4. This is good to the 10th, which is 4 zig figs. And this one is good to 3 zig figs. So I'm going to round to 3 zig figs. So the molar mass is 106. But what was the question?
The molecular formula.
So we're going to say that matches this. So the molecular formula is C8H10. So I would actually expect to see all of this as part of your answer.
Wouldn't we or couldn't we divide this molar? I'm trying to think of the steps to get the molecular formula. So if we're given the empirical, then we would divide the empirical molecular
Right. So
by
here
the multiplier.
we would do 106 divided by 53, which means the multiplier is 2.
Two.
Then we would take C4H5 and multiply it by 2, which would be 53 times 2, which is C8H10.
Okay.
So this is the way you do it if you're not sure if the molecular formula is going to be close to the empirical formula.
Right.
But this is the other way to do it. Just make a list of all the possible molecular formulas it could be and choose the right one. Okay, so it works the same either way. This is just another way of thinking about it. And this way is almost better for you to think about it because you can see that the molecular formula is some iteration of the empirical formula. Are you with me there? Okay, this almost makes it too abstract. So if this is abstract, then this is stract. Is that? You know what I mean. Because doesn't ab mean the opposite or something like that? Abnormal?
Yeah,
So
not,
if this is too abstract, then this is stract.
okay.
Feel free to use that on someone somewhere down the line. Someone starts describing something to you and say, well, then you say, hey, that's too abstract for me. How about getting a little stract? And they're going to look at you and say, you didn't take a class with Tony, did you? Because he would always say stupid stuff like that. Okay. Acetaldehyde is a common liquid that vaporizes readily. Determine the molar mass of acetaldehyde using the following data. This one just screams out.
Mhm.
Density is equal to PM over RT, which is little m over V, depending on what we want here, right? And here's the data they give us. So here, the molar mass, we're going to do molar mass is equal to dRT over P, right?
Yeah.
So for the density, we're going to take our 125 milliliters, and I'm going to convert this a little differently this time. I'm going to multiply by 1 liter over 1,000 milliliters. And get 0.125 liters. So for the density, and you might even want to write this here for density. Density is mass divided by volume, because it might help you to put in the proper numbers here for mass and volume. So we have 0.107 grams over 0.125 liters. I'm going to leave the R off until I know what my pressure is. My T is going to be, well, 273.15 K, right?
Yeah.
That one's easy. And then my pressure is going to be 331 millimeters of mercury, which makes me want to use the 62, 0.37 liters, millimeters of mercury per mole per K. So we can see that the millimeters of mercury cancel, the K's cancel, the liters cancel, and we'll be left with grams per mole, which is what we want for molar mass. Now, I'm going to tell you the formula for acetaldehyde is this: CH3C double bond OH, which means it weighs 24.02 for the carbons, 4.04 for the hydrogens, and 16.00 for the oxygen, which is a total of 44.06, right? So I'm predicting that the answer should be 44.
Okay.
Now let's estimate the answer. How do you want to estimate this one?
62 into 331.
How many times does it go into 331?
5 times?
Okay, 5, great. Now what do you want to do with the 5 down here?
Oh, I don't know.
Well, why don't we divide 5 into 273? Why don't we
Yeah.
make that 300?
Okay, so 60.
60. Okay, now here, 0.107 or 0.125 is really close to 1, agreed?
Mm-hmm.
But it's not. It's more like 0.8. So what's 0.8 of 60? 50, right?
Yeah,
50-ish. So we're saying 50-ish. Now, you just came up with 50-ish, right?
I would say you did, but yeah.
Well, I think we did it together. And what do we know the answer is supposed to be?
44.
And we were not thinking 44 when we were doing the estimate, were we?
No.
And we still got close to what the real answer should be. So that should give us some confidence, if you will, in our estimate. And let's see what we get. Now, how am I going to put these into my calculator? I'm going to do 0.107 times 62.37 times 273.15 divided by 0.125 and divided by 331. And I can see I had a problem there. I did 3,331 and I knew I'd get the wrong answer. So I get 44.057.
You get
58 actually. And here we have 3 zig figs, 3 zig figs, 4 zig figs. This one is 0.0, so 4 zig figs and 3 zig figs. So my answer ends up being 44.1 grams per mole. So I'd expect to see this work on an exam if a question like this were asked. You can't have shown me this because you don't know the formula.
right.
Okay, any questions about this one?
Nope.
Okay, let's try number 32. Okay, silane, CiH4, reacts with O2 to give silicon dioxide and water. A 5.20 liter sample of silane gas at 356 millimeters of mercury pressure and 25 degrees Celsius is allowed to react with O2 gas. What volume of O2 gas in liters is required for complete reaction if the oxygen has a pressure of 425 millimeters of mercury at 25.0 degrees Celsius? So we're going to try this problem one way and then we're going to try it another way. So the first thing we're going to do here is we need to realize that if we want to get the volume of O2 gas in liters, that we probably want to do this. PV equals nRT. So that means the volume is going to be nRT over P, right?
How did you know to go with that one?
Well, because the other one is to use P1V1 over N1T1 is equal to P2V2 over N2T2, right?
Yeah.
Okay, so we have a 5.2 liter of silane gas is allowed to react with O2 gas. Okay?
Mm-hmm.
What volume of O2 gas in liters is required for complete reaction? So here's my O2 gas that I want to react with the silane, right?
Yeah.
Is anything happening to that O2 gas before we react it? Are we changing the volume, changing the mass, changing anything about it?
No.
So we're really asking, how much of this do we need to react with our 5.20 liters of silane?
So since nothing's changing.
Yeah, if we were going to say we have the oxygen in a container at high pressure, we're going to release it to react, then we would be doing a change.
Okay.
But when you can't identify something in here changing, like this is, oh, when the pressure changes, we don't need to do this. We're going to do this.
Okay.
So I'm going to put O2 here just to remind me that I'm going to get the volume of O2 gas. So I need the moles of O2 gas. I need R, which I can get anytime I want, right? I need the temp, which they give me right here, and I need the pressure.
Okay.
But how am I going to get the moles of O2 gas when I don't know the volume? right?
So molar
I mean,
mass.
I'm sorry. I want the volume, but I don't know how many moles. So I do know that if I have the moles of silane, I should be able to get the moles of O2, correct?
Yeah.
Because clearly, if I have 2 moles of silane, I'm going to have 4 moles of O2.
Right.
If I have 1 mole of silane, I'll have 2 moles of O2. So if I can figure out how much silane I have, I can figure out how much O2 I have mole-wise. So that
Okay.
brings me to the idea that using the same equation for silane, I can figure out the moles of silane by taking the PV over RT for silane.
Okay.
Right? So once I get this amount, then I can get that amount, then I can do that. I can do this in 3 parts. So do I have the pressure, the volume, and the R and T for silane? Oh,
Yeah.
I have the volume, I have the pressure, and I have the temp. Fantastic. I can do this step by step. So I'm going to put a 1 here, a 2 here, and a 3 here. And actually, I can combine 1 and 2 together, as you'll see in just a moment. So let's do number 1, the moles of silane. And actually, I'm going to put moles of O2.
I
So
thought
I'm going to put that as equal to, what is the pressure of silane? 356 millimeters of mercury. Okay. And the volume, 5.20 liters, right? The R, we're going to use the 62.37 liters, millimeters of mercury per mole per K. Why are we using this one instead of the 0.08206?
so they cancel.
So that the pressure units cancel, absolutely. And the temperature here of the silane gas is 25, which we know is 298.15 K. Now this is actually going to be moles of silane. So I would want to multiply by, actually, you know what? I'm going to keep this as N of silane and do this as 3 parts because it'll make more sense to you that way. So let's estimate the answer. How do you want to do this one?
We could go 62 into 356 again.
How many times?
Was it 5?
Okay. What do you want to do with that 5?
Times it by 5,
And what do you get?
25.
Now, doesn't this go into 356 a little more than 5 times?
Yeah.
So isn't this number a little more than 5?
Yeah.
And what's a little more than 5 times a little more than 5? It's not 25, is it?
Right.
What is it?
30.
Oh, great. What's 30 divided by 300?
It point 10, 0.1.
0.1. So we should get an answer of 1/10.
Okay.
Let's find out. Okay, what did you get? And we get 3 zig figs on that if we were done.
Um, 0.099.
Okay, 0.09955 moles. And if we rounded it to 3 zig figs, it would be well, what is this 5 turn this 5 into?
A 1.
Turns it into a 6, right?
Yeah, and then
996 moles.
mhm,
And that's compared to 0.100 moles, which is almost the same number here. I mean, you said 0.1, right? Look
yeah,
how different they are. That's like saying 996 versus 1,000. Not very, so excellent estimate. Okay.
mm,
Now, to get the moles of O2, so that's number 1. To get the moles of O2, we're going to start with 0.09955 moles of silane and multiply by 2 mole of O2 to 1 mole of silane. And where do I get those numbers from? 2 to 1.
the balanced equation.
Right. And
Yeah.
so what's neat about this is I don't need to change anything in my calculator. I just do times 2. So I get 0.1991 mole of oxygen. And now I can do equation number 3, which is that the volume of O2 is equal to the moles of O2, 0.1991 mole of O2, times R, which I'm going to leave off for just a moment, the temperature, which we say is 25, so that's 298.15 K. And the pressure is 425 millimeters of mercury. So I'm going to use the 62.37 millimeters of mercury per mole per K to get that volume of O2. Okay. How about we estimate this answer?
Um, we could say 298 goes into 425, a little less than 2.
Yes.
Like, I don't know. Um,
Now, when it's that hard for you to do, maybe we should try something else. How about how many times does 62 go into 425?
um, I don't know.
Let me give you a little hint on estimating. You see how this is 62 and 425?
Yeah.
I'm going to get rid of the ones, and I'm going to get rid of the ones here. How many times does 6 go into 42?
7.
7. So this is a little trick in estimating.
Yeah.
You get rid of the ones on both of them, or you get rid of the ones and the tens on both of them.
Okay.
A little trick. So now you got 7. How many times does 7 go into 298?
A lot.
A lot. And here you can actually do this. How many times does 7 go into 29?
3, 4 times.
4 times with 1 left over, right?
Mhm.
And then you have 18. How many times does 7 go into 18?
2 times.
What was that?
7 goes into 18.
Yeah,
A little more than 2.
almost 3, right?
Yeah.
So you could say 43.
Okay.
And what's 43 times 0.19? Well, I don't know, so I'm going to say it's 40. What's
Yeah.
40 times 0.2?
Um,
Well, what's 4 times 2?
80.
So you
So
got to decide, is 40 times 0.2 8? 80, 0.8, 800. Which one of these is it?
Well,
It
it
can't
would
be 80 because you can't multiply by 0.2 and get a bigger number, right?
right. So it's going to be 0.8.
0.8 would be too small though, right?
Yeah.
Because if you multiply by 0.1, you'd get 4, wouldn't you?
Yeah.
So it's got to be 8.
Okay.
Okay, so we're going to estimate the answer is 8. Or not, did I say 0.8? I said 8, right? Oh, it's 8.71. Now, what are the units?
Nope. Well, we're looking for volume, so it should be liters.
Okay,
Yeah.
the moles cancel, the K's cancel, the millimeters of mercury cancel. The only thing we're left with is liters, so we do get liters.
Yep.
So in this problem, a 5.2 liter sample of silane reacts with O2 gas, and we get 8.21 liters of oxygen. Okay?
Okay.
So it turns out I wanted to show you a trick to use to do with this one, and there's no real trick to use with this one.
Okay.
Okay, cool. Okay, it's 2:44. Do you have time for another one, or do you want to call it quits?
We can do one more.
Okay, let's do one more. The hydrocarbon octane burns to give CO2 and water vapor. And here we have a balanced reaction. I'm assuming it's balanced. We can double check, but I'm pretty sure it's okay. If a 0.048 gram sample of octane burns completely in O2, what will be the pressure of water vapor in a 4.75 liter flask at 30 degrees Celsius? So can you see here, we want to calculate the pressure of water. So we're going to use PV equals nRT. And so the pressure of the H2O gas is going to be nRT over V, right?
Yeah.
And we are given the temperature of the water vapor. We're given the volume of the flask. We know what R is, but we don't know how many moles. So how are we going to get the moles of H2O? Well, if we had the moles of C8H18, we could calculate the moles of H2O that we're going to make, right?
Yeah.
But we're not given the moles of C8H18. What are we given?
We're given the grams of octane.
So if we can take the mass of C8H18 and turn that into moles of C8H18, then we'd be in business.
Okay.
Is there a way for us to do that?
Yeah, using the molar mass.
Okay, so we're going to do a 1, 2, 3, correct?
Yeah.
Okay, so number 1, I'm going to take 0.048 grams of C8H18 and multiply by 1 mole of C8H18. And the molar mass of C8H18 is going to be 8 times 12.01. Plus 18.18. So I get 114.26. So this one is a tough one to estimate, but we can at least do this. What is our answer going to be here compared to what we start with? And my answer would be, I'm dividing 0.048 by 100, so I expect the answer to be 0.00048. I'm going to add 2 zeros because I'm dividing by 100.
Yeah. And small.
And it should be even less than 0.0048 because I'm not dividing by 100. I'm dividing by something a little bigger. So I can estimate 0.00045 or 40, something like that, right?
Yeah.
And indeed, I get 0.000420. And this is only good for 2 zig figs because of the 0.048.
Right.
Okay, so that's equation 1. Number 2, I'm going to get the moles of H2O. According to the balanced reaction, 25 moles of O2, right?
Yeah.
And 2 moles of C8H18. Now, can we estimate this answer?
Mhm.
Can we estimate this answer?
Yeah.
Doesn't 2 go into 25 like 10 times?
Yeah. So
A
maybe
little more. What's 10 times this?
10
My
times.
answer would be, instead of 3 zeros, I'd only have 2, right?
Yeah.
So 0.004. And since this is a little more than 10, it's going to be 0.0045 maybe.
Yeah.
Actually quite a bit more, 525 mole of O2. So I underestimated a little there, but we did get the 0.00 down right, correct?
Yeah.
Okay, for number 3, we're going to use that the pressure, oops, I made a mistake. What mistake did I make here?
We're not looking for pressure. Oh, yeah, we are.
It's not O2.
Oh, yeah,
So
we need.
I got to cross this out and write H2O. And what do I write here instead of 25?
18.
Okay. And actually, when we think about it, 2 goes into 18 9 times. 9 times this should be pretty close to 0.0042.
Okay.
0.00378. Okay, so what is the pressure of the water vapor? And what keyed me to this being wrong is this right here.
Right.
I wrote that I want the pressure of H2O, and I'm looking here and I have the moles of O2. I can't use the moles of O2 in this equation. I need the moles of H2O.
Right.
And so the label helped me figure that out and say, oh, whoops, ruh-roh. Okay, so now our moles are 0.00378 moles of H2O. I'm going to go ahead and jump to the pressure since they say the pressure. Oh, actually, we can use whatever R we want.
We can.
Yep, the temperature is going to be 273.15 plus 30, which is 303.15. And the volume is 4.75 liters. Okay. So the question here is, do you want your pressure answer to be in liters, or excuse me, millimeters of mercury, or do you want it to be in liters? I'm atmospheres, I'm sorry.
Okay. I guess
Which one do you want?
atmospheres.
Okay, then we're going to use 0.08206 liters atmospheres mole K. Now I'm going to be honest, this is going to be a tough one to estimate, but we can give it a try. So one of the tricks I like to use is 0.0826 is 0.1 or 1/10. Why do I like 1/10? Because I can do 1/10 of anything. It's real easy. What's 1/10 of 300? 30.
Mm-hmm.
Okay, so I now have 30. What's
Okay.
30 times 0.004? Well, here's one of the things I like to do is what is 3 times 4? Or what is 4 times 3?
12.
Okay, so here I'm trying to do 0.004 times 30. And I know it's going to be equal to 12, but I don't know if it's 12, 1.2, 0.12, or what, right?
Yeah.
So we have to think about this a little bit. And here's a little trick. I'm going to move that over 1 and that over 1, opposite directions. So now I have 3 times 0.04. I'm going to move that over 1 and that over 1. And now I have 0.4 times 0.3. And I know that that means whatever answer I get, it's going to be move the decimal over 2 times. So I get 0.12.
Yeah.
So that's just a little trick. That's a tough one to use when they're so small. So what's 0.2 divided by 4.75? Because we never dealt with that. About 0.02. And the way I'm doing this is 5 goes into 1 0 times, 5 goes into 12 2 times, right? So 0.02. Now, honestly, I probably would have gone with the 62.37 because it's easier to estimate with bigger numbers than with small numbers.
Yeah, I see.
Okay, let's see what we get though. 0.00378 times 0.08206 times 330.15 and divided by 4.75. Ooh, and we get 0.0216. And what are the units here?
Atmosphere.
Atmospheres. So this is all the work we'd have to show for what is the pressure of the water vapor.
Okay.
Not very high, is it?
No.
Okay. If the O2 gas needed for complete combustion was contained in a 4.75 liter flask at 22.0, what would its pressure be? Now, how do we do that one?
Would we do the same thing but use a different temperature?
Let's see. Yes, we would.
Is that what it's asking? Just what
So,
would be if the temperature was different?
yeah, so we would do number 1. We'd have 0.000420 moles of C8H18. Then number 2, we would take our 0.000420 moles of C8H18 and we would go back and multiply by 25 moles of O2 to 2 moles of C8H18, which we mistakenly did up here, and we already know is 0.00525 moles of O2. Oh, and by the way, this answer should be 0.022 atmospheres because of this up here only has 2 zig figs, which means this only gets 2 zig figs, which means this only gets 2 zig figs.
Why? Okay. Why are we finding the moles of oxygen?
Well, because we're doing the same thing as we did over here. We're going to use the mass of this to get the moles of oxygen. Then we're going to use the moles of we're going to use the mass of this to get the moles of octane. We're going to use the moles of octane to get the moles of oxygen. Then we'll use the moles of oxygen to get the pressure of oxygen.
Okay.
So here, the difference is that for the pressure of oxygen, like you said, we're going to use the same equation. The moles will be different, but also the temperature will be different.
Okay. Right.
And do you want to use atmospheres again? Because our first answer is in atmospheres, and it'd be nice to compare the two.
Sure.
Okay. And here the temperature, do you see how it's 22 degrees?
Mm-hmm.
So that's going to be 295.15 Kelvin. And the volume you can see is 4.75 liters. Now, can we estimate this answer?
You can.
You can too. And here's how we do it.
Okay.
Isn't this problem just like the one we just did?
Yeah.
So how different is 330 versus 295?
Not a lot.
Not a lot. How different is 0.00378 versus 0.00525?
Not a lot.
Not a lot, right? A little, but not a lot. So wouldn't you say that our answer should still be around 0.022?
Yeah.
Okay, but my estimate would be that maybe this is a little bit bigger than that compared to this being a little bit smaller than that. So my guess is a little bit bigger than 0.025.
Okay.
Maybe 0.025. Maybe I said that wrong. A little bit bigger than 0.022. So I'm thinking 0.025, 0.030, something like that, maybe. So the thing about estimating is you don't have to do it from nothing. You can do it from stuff you've done before also. Does that make sense?
Mm-hmm.
Okay, so did you already plug the numbers in?
Nope. Work on it. Okay. It is a little bigger.
So I get 0.027 atmospheres with 2 zig figs because this 0.00525 is only good to that second two.
It is? Okay.
Yeah, because of the way we calculated it. This is only good to that two, which is 2 zig figs. So when I use this here, this is only good to 2 zig figs. So when I use this here, this is only good to 2 zig figs, but we don't round till the end.
Okay.
So we would expect to see this additional work. We don't need to calculate the moles again because we already did it, right?
Yeah.
So I mean, the moles of octane again,
Yeah.
but we would show the calculation for the moles of O2 and the calculation for the pressure of O2. Fair enough?
Yeah.
And that's number 34. And that's probably a good place to stop. We've been at it for a while.
Okay.
I'm sure you're tired of listening to me. Because I'm tired of talking.
All right. Thank you.
You're welcome. Will I see you tomorrow?
Yep.
Or am I going to see you at 6?
No, I'll be on tomorrow
On the what?
at 10. Tomorrow morning.
Oh, you'll be at 10. Okay. Yeah, I was a little late today because I was watching the news and waiting for that verdict on the Derek Chauvin case.
Oh, okay.
All right. You have a good evening.
You too. Bye.
Bye-bye.